Okay, so I welcome the students who have enrolled in this course, Applied Thermodynamics, to this live session. Enrolled students, learner of this course, Applied Thermodynamics, who are attending this live session, I request all of you to post your question in the chat box if you have any, primarily from the steam power cycle part, so that we can discuss them now. I welcome you all to this live session. Particularly if you have any questions from the steam powered cycle of this course, I request you all to post your question in the chat box so that we can start discussing them now. We have discussed about steam powered cycles, basic cycles, modification of steam powered cycle. Then we have also discussed about steam generator, steam turbine. If you have any questions from this module of this course, you may post those questions in the chat box so that we can discuss them now. If you have any questions from the other modules of this course, my colleague will join shortly in this session and he will interact with you all to address all those questions. But if you have any questions from the steam power module of this course, kindly post your question in the chat box and we can discuss. If I recall correctly, we have discussed about, steam power cycles, starting from the Carnot cycle, then Rankine cycle, modification of Rankine cycle. Then we have discussed about the steam generators, their working principle. We have also discussed about steam turbines. So if you have any questions from this particular module of this course, kindly post your question in the chat box so that we can discuss them now. We have discussed about the limitation of the Carnot cycle. We have also discussed about, which is one of the most important ideal cycle. And then we have discussed about the ideal simple Rankine cycle. From there, we have estimated the thermal efficiency, identifying the limitation of this particular cycle. We have also discussed about several modifications, and we have seen that efficiency can be increased. And we have also discussed about demerits associated with each of the modifications. And finally, we have discussed about the regenerative Rankine cycle, and we have seen how because of this regeneration, we can increase the thermal efficiency. Then we have discussed about steam generators. We have identified several modules of these or several components of steam generator. The working principle, different flow cycles of steam generator. We have also quantified the boiler efficiency. We have solved numerical problems. And then we have discussed about steam turbines, different types of steam turbine. Then their, blading diagram. Then we have estimated the blading efficiency or diagram efficiency. Then we have also discussed about pertaining to the impulse turbine, why multi-staging is done, why compounding is done, We have also solved a few numerical problems from this part, that is steam turbine part. So if you have any questions from this particular module, then we can discuss now. If we increase the net work output, does it increase the efficiency also? In reheat, do we increase the power output or cycle efficiency? See, you have to be careful. If you increase the net work output, so if you try to remember the thermal efficiency is net work output by heat input. So you have to be careful at the cost of the increase in net work output, whether you are going to have substantial increase in the heat input or not. Maybe you are increasing work output, that is true. To get such an increase in work output, if you also need to increase the heat input, then perhaps efficiency will remain same. Sometimes it may also decrease. So increasing the net work output, if it is net work output, then it is fine, because W net equal to probably you have, I mean, if we consider the thermal efficiency, W net equal to QH minus QL. So if it is Q in, QH equal to Q in and QL is equal to Q out. So Q in minus Q out is equal to W net. Now, if we can somehow increase the W net without increasing Q in, then efficiency can be increased. In reheat, do we increase the power output or the cycle efficiency? See, you know that we have discussed about if we try to increase, if you try to recall the reheat cycle, you know, how many stages of reheating you would like to have. Single stage reheating, double stage reheating. So what we are essentially doing, you know, using reheating, we are increasing the quality of steam leaving the turbine. Also, if you try to recall the TS diagram, then you'll find that the area under the process line, that is W net, is increasing. If W net is increasing, then efficiency will increase. But again, we have to be careful that to get that W net, what is the Q in? So these two things, that is W net by Q in. So if we increase W net, only criteria that the efficiency will increase, that we can't say. So basically we have to be careful that when we are trying to have more work output, net work output, what is the heat input to the cycle? To get an increase in W net, are we going to have substantial increase in heat input? If it is the case, then it has no meaning that we can increase the efficiency. I would, so since you have raised this question, let me discuss reheating. That most beneficial part of this particular mechanism is that we can increase the quality of steam at the exit of the turbine. So if we increase the quality of steam, that turbine blade erosion problem can be avoided, because if the steam is having high moisture content at the exit, then corrosion problem would be there. So to prevent that particular effect, we need to increase quality of steam at the exit of the turbine. Reheating is the way by how we can increase the quality of steam at the exit of the turbine. Not only that, so if we try to recall that if we bleed steam from the high pressure stage turbine, if we take that steam to the boiler again, if we reheat it, and then we can take that steam and we can allow that steam to flow through low pressure stage turbine. And finally, we are getting steam out from the low pressure stage turbine. And from low pressure stage turbine, that steam is taken to condensate. So this is a kind of reheating stage. Now, so basically, you know that such a reheating mechanism, we are not going to have additional heat input. Instead, we are bleeding or we are extracting steam after it does work in the high pressure stage turbine. Then we are taking that steam to the boiler. We are reheating that steam. We are taking to the low pressure stage turbine. So while steam is expanding in the low pressure stage turbine, then it also does work on the rotating part of the wheel. So we are getting work output. Not only that, we also can increase the quality of the steam. So reheating can have two beneficial aspects. One is it increases the quality of the steam at the exit of the turbine. Turbine blade, I mean, if moisture content is more, then the turbine blade might get some kind of, problematic issues that and also we can increase the work output. There are several other methods I have discussed by how we can increase the efficiency or net work output. Those are the modifications of simple Rankine cycle, that is, reheating. I mean, that is the superheating the steam, then lowering the condenser pressure, and finally increasing the boiler pressure. So if we try to recall again, just try to recall the TS diagram, we'll find that by increasing the boiler pressure, we can increase the net work output, but the quality of steam should be compromised at the exit of the boiler. So again, we have to be very careful. Similarly, if we try to reduce the condenser pressure, so we can have an enhancement of W net. So efficiency can be improved, but again, problem associated with turbine blade, kind of with high moisture content of steam will be there. So these two avenues, though, can be useful to have more or enhanced work output, net work output, but at the same time, these two ways are going to invite additional issues of turbine blade corrosion problem. So only one modification, that is superheating steam, can be implemented, that we have discussed. It not only increases the net work output, but also increases the steam quality at the exit of the turbine. But again, the designer should be careful while he or she is designing the steam turbine or steam power unit, that the selection of blade material should be such that the blade would be able to withstand such a high temperature. Otherwise, again, some mechanical problems will be there, like development of thermal crack within the blade. So all these problems are associated with all these modifications. We have discussed all these. And, accounting for these issues, reheating is an important, modification. Nevertheless, we have also discussed that cost associated with one reheat stage should be justifiable with the enhancement of efficiency from the cycle. So that means the mechanical arrangement that is needed to have at least one reheat stage and cost associated with that mechanical arrangement should be, less than the efficiency you are going to have with this additional reheat stage. So it is seen that, that more than 3 reheat stages are not, recommended. Considering this, though there are several avenues we have discussed in the class, those we have already discussed in the class, like, increasing boiler pressure, lowering the condenser pressure, superheating the steam beyond the saturated point, and also the reheating stages. The most important and rather economical way of increasing the cycle efficiency is regeneration. We have also discussed, taking 2 different cases. In one case, we have discussed about open type feed water heater. And in second case, we have discussed about closed type feed water heater. In these 2 cases, we can increase the feed water temperature by the method of regeneration. And we have seen that we, adopting this regenerative method, we can increase the cycle efficiency. So we have discussed all these aspects in the class. Then we have solved a few numerical problems. Then we also have discussed about the steam generators, boilers, which is one of the most important components of the steam power cycle. And we have identified several components of steam generator or boiler. We have identified different flow cycles, that is, flue gas cycle and steam water cycle. We have also discussed about the, trivial, non-trivial aspects. So both trivial as well as non-trivial aspects we have discussed. And pertaining to this particular, part, that is boiler, we have discussed about the boiler, types, that is water tube boiler and fire tube boiler. We have also solved one numerical problem. And then we have discussed about the steam turbines, because if you try to recall, there are several, components. Steam is generated in a steam generator or boiler. That steam is taken to the turbine. It is not a case that steam is directly taken from boiler to the turbine. Instead, steam is allowed to flow through nozzle, and then steam which is coming out from the nozzle, which is having high, velocity, that steam is taken to, flow through the turbine blades. That high velocity jets, which is, the high velocity steam jets strike the turbine blades and jets get deflected and by virtue of momentum difference, the turbine blades spin, and we are getting work output. So we have also discussed about flow through the nozzles, and finally nozzle efficiency as well. And then we have discussed about the basic cycle, and that I was discussing in today's live session. So I request you all, if you have any specific question from this module of this course, please post that question in the chat box so that we can discuss them now. This, live session is limited to 1 hour. My colleague Professor Sahoo will join shortly to discuss with you all. If you have any question from remaining modules of this course, so I request you all to post your question in the chat box quickly so that we can discuss. Of course, the questions should be from the steam power module of this course. Since this session is limited to only 1 hour, I will be here for another 3-4 minutes. I request you all to post your question in the chat box so that we can discuss those questions now. Let me tell you, if you have any questions from the steam power module of this course, like steam power cycle, steam boiler, and then flow nozzle and steam turbines. So I request you all to post your question quickly if you have any. Otherwise, my colleague Professor Sahoo will join the session soon. What I can see, there is no question. So I thank you all who are attending the session, and the session will be now continued by my colleague Professor Sahoo. Thank you.
Okay, dear learners, I welcome you to this live session for my part. This is the last live session for this course. I request you to pose your queries for my part, but at the same time, during our discussion forum, we came to know some of the queries raised by the learners. And I just want to share that. So the first question was given by this with reference to lecture number 30, numerical question number 1. The question, apart from that problem solving in other parameters, one of the parameters which includes the calculation of entropy change. That entropy change is for a given state and entropy change at the dead state. And difference in entropy needs to be calculated. So while solving the problem, we have used these equations that involves the concept of absolute entropy, where the based on the data table, it is easy to calculate the values of absolute entropy from the table itself. And the expressions was used by that for that particular parameters. But the learner's question was that this entropy change, one can find out the entropy values with reference to TDS relations. That is also true, and we can do this exercise and try to see that based on these TDS relations and based on this concept of absolute entropy, we can find out how much difference we are getting. So, and we are insisting on this absolute entropy because this is more accurate than this conventional method of calculation of entropy. So basically, the summary just I want to say is that change in the entropy is a function of thermodynamic states of temperature and pressures. So in other words, the system goes from state 1 to state 2. The change in entropy is S1 minus S2, and for this S1 and S2 is related to temperature and pressure. So this is the entropy equations we have already. We all know these things. Now in this particular problem, one of the state is dead state, that is S0. Other state is the absolute state. Other state is the any arbitrary state. So entropy calculation was taken care. And there is a term called as, and in that equations, there is a pressure term and temperature term. And this pressure and temperatures term, the expression, since when you calculate the entropy on mass basis, whatever equations we have been used to it, that is fine. But when you calculate the entropy on the molar basis, we have to use the values of R bar, which is universal gas constants. So, so what we can say, the dependency of entropy change with respect to temperature and pressures, pressure needs to be evaluated. In one case, we are considering the simple root as a concept of absolute entropy to calculate the change in entropy due to temperatures. Other one is the entropy calculation change due to pressures. So this is what we have used it. And that problem, it is used. However, it's a very lengthy problem, and it is and for this problem, it is just a matter of the calculations. So the learners are requested to go further and deep into it. The second question was based on lecture number 37 for problem number 3. which talks about that, which is the question was compressor is a work consuming device. So the actual work is always greater than theoretical input. This is true. So actual work is the ratio of theoretical work to compressor efficiency. This expression is true. But with respect to the problem that we have asked for, here we are looking at the one air conditioning plant which is operated at 40 ton of refrigerations, and here the the 96% efficiency is not the compressor efficiency. It is the actual. It is the efficiency. It is contractor actual compressor efficiency. It is mainly the which is the power which is being received by the compressors. So this is so that is the reasons the work load is calculated based on 46 when it multiplied by 0.96. Okay, so these two questions was raised. If you have any more queries, please pose them. We have another 15 minutes time. Please pose your queries. So the questions that needs to be asked in the examinations are like this. First category is multiple choice questions. So in this type of question, there will be 4 options will be given and one option is correct. So the marks will be awarded for the correct options. And in this category, we'll have a conceptual question, recall type, uh, mm, all these things. Second category of questions is multiple select questions. So in this type of questions, there will be more than one options might be correct. So the marks will be awarded only when all the options are correct. So this is the second category of the questions, which is similar to multiple choice, but more than options might be correct. Third category is that you will be given a statement. We need to say whether it's a true or false. So this is so you have to so on that basis the marks will be awarded. Fourth category of questions will be there will be a simple numerical problems given to you and you need to find out its answer. So the numerical answer has to be given in your from your end. And for fifth category of questions are like common data question. Common data question means a statement will be given. In that statement, all the data parameters are given. For example, in an auto cycle, if I say auto cycle problem, so there I need to calculate what is a brake thermal efficiency, what is power output, what is all these things. So these are for common data. These are the type of the question that we will have. So how many questions will be? There will be on an average, you can expect about 60 to 70 questions will be in total. So each section, if you say on an average 15 to 20 minimum question will be there. And of course, each question like 1 mark questions, you recall type questions where you do not have to spend much time. Time will be spent only when you are solving a numerical problems using your calculator or calculators. That time will be consumed. Of course, uh, so these are my answers for your questions. Any more queries? Okay, thank you very much. You have attention. Mukesh, I wish all the best for your exam. Any other questions? Exam duration will be 2 hours or 3 hours. It all depends. I think it will be 3 hours. It all depends on the NPTEL's framework. Whatever framework they will give, you have to stick to that. Okay, thank you. Okay, thank you very much. I wish all the best for your exam. And we also wish success for your future. I hope this course will be beneficial to all of you in terms of credit transfer, in terms of high-end research, and so many things. I hope all of you will get benefited and you have enjoyed this course. Uh, mm, and with this, I thank you very much for your attention over the entire period of time, and my best wishes and success for your future. Thank you for your attention. Now with this, we are closing this live session.